let's get started. Good afternoon, everyone. My name is Victor Cabrera, and I'm a professor and extension dairy specialist of animal and dairy sciences at UW-Madison, and I'm going to be co-moderator of this track today with Jeremy Foltz. Before we get into the session, we have divided our time into two themes. First, we will be highlighting two projects focused on dairy farm economics. Then in the second hour, we will be showcasing two projects that represent new income streams and added value to the dairy industry. Each speaker will have 20 minutes, and after each speaker, we will have about 5 minutes for questions and keep the discussion going. With that, my co-moderator, Jeremy Foltz, will get things going on as our first speaker. Jeremy Foltz is a professor of agriculture and applied economics at UW-Madison. His research focuses on the economics of farm structure and technology adoption in the US, elsewhere in the world. So let's welcome Jeremy.
Thanks, Victor. So I'm here to talk about actually maybe something that's not that happy, the exit of dairy farms. This is joint work with Talita Silva, who's here. She did all the good parts of this, and I'm responsible for the things that you disagree with. So that's why I'm up here, so you can argue with me. All right, so if you look at just dairy farm numbers, the state of Wisconsin has been losing dairy farms at a great rate since 2003. Wisconsin has lost more than 50% of its dairy farms. When I first came to this university to work on these kinds of problems, I could have put up pretty much a similar slide that said, oh, in the last 20 years, we've lost 50% of our dairy farms. And so that trend has continued. At the same time, the number of cows has stayed fairly stable at about 1.3 million cows. And the total production of milk has gone up. The total value of what's being produced on these dairy farms has gone up. But this issue of like who's staying in business, who's going out of business is something that we're going to think about today. So what are the determinants? So what are the characteristics that make a difference between dairy farms that stay in business and dairy farms that exit? And then the other thing we're going to do is sort of more a methodological thing, which is, can we predict who's going to exit? And the way in my world as an economist we would do that is we would do a survey. We'd ask people like, oh, how long are you going to stay in business? And and if people are accurate, well, then, okay, we can learn something today about what's going to happen tomorrow. That's, a whole lot of the whole scientific endeavor is that, right? Like, what does climate change look like in the future? So we're going to look at this using some data that we collected earlier. So here, just, this is the number of dairy farms. This is total milk production. That's, well, since the 1930s, but basically that's what's been going on for a very long time. So what does the literature tell us about this? Back in 2004, I did a paper that looked at dairy farm exit in the Northeast, where there were some price policies to try to keep dairy farms in business. It turned out that those policies had a very small effect. In Europe, income and government intervention has done things to reduce dairy farm exit. The Europeans in general are much more active in trying to keep farms in business. Generally studies of exit suggest that among Canadian farmers, older Canadian dairy farmers are more likely to predict they're going to exit. The economic environment and farmer characteristics influence exit decisions. In Japan, which is admittedly quite different than the situation in the US, We find off-farm work opportunities help keep farms in business. And so these are things that we are actually able to test some of these. So we have a survey in 2003 where we did a survey of dairy farms in Wisconsin. And so we have the characteristics of those respondents that give us this sort of initial condition. Okay, what were those farms like? How many cows? Did they have off-farm work? Those kinds of things in 2003. And then we're going to look at them again in 2016 from the licensed dairy producer list and see if, okay, is that farm still there? And we're going to allow that farm to, change ownership. Like you might have children operating that, but we're going to see, is there a licensed milk producer at that location? Or I don't know, we had some band around there still in business today. And we can basically localize each of the farms. So this is just a map of the dairy farms that were there in 2003 and whether they exited in 2016. So blue circles are farms that stayed in business. Red X's are ones that are no longer there. And this is kind of a Rorschach test for you. Do you see a geographical pattern? Do you see something obvious like, oh, this part, I would have expected lots of exits or farms more likely to stay in business? Like, maybe there's something different going on in the Southwest, or maybe this area around Green Bay or around Wausau. I can tell you, at least personally, my Rorschach test of this is like, I don't see a pattern there. And actually, the news is when we test that statistically, we will not find a geographic pattern, which is kind of important information, right? But okay, so the way we're going to do this is an econometric equation that is our dependent variables, a dummy variable that takes the value of 1 if the farm exits by 2016. And then these are the initial characteristics from 2003. How old the farm owner was, the number of cows, average milk produced per cow, how important the dairy business was in the total cash on the farm. That is, how important, how much are they specialized in dairy as opposed to other operations, and whether it's a corporate business or not, and then also whether they're a grazing farm. And then we have various region level fixed effects and a robust standard error that, so just so in 2003, the average farmer was just under 50 years old. The average farm size was 83 cows, and what's that? I guess daily milk production 61 pounds. Most of them were, and we had about 22% grazing farms. Okay, so here's the main result, which I think easiest to sort of look at this in this way rather than the numbers. So older farmers were more likely to exit the business. So that makes sense. You're 80 years old, like maybe you have people who take it over, but more likely you're going to sell off. More cows, less likely to exit the dairy business. More productive cows, less likely to exit. And more focused on dairy, also less likely to exit. This was something we weren't sure about, right? Having a highly diversified farm, we know that the dairy industry is volatile, and you can have 2 or 3 years of bad prices or low prices. And so perhaps being more diversified would help. We find the exact opposite. We see no effect of whether it's a grazing farm, and how you organize your farm business makes no difference. Now, if you know the dairy business, whether it's a family farm or you have an LLC is probably more to do with, how good your lawyer is, or what your accountant told you was the best way to organize things. But anyway, it's not that, one of those forms is better than the other. So that's basically our main result. Like the difference between a 50-year-old and a 60-year-old owner in 2003 increases the likelihood of exit by about 8%. The difference between a 50 cow and a 150 cow operation would decrease the likelihood of exit by about 4%. So not actually that big, right? We find these effects. Yes, they are statistically significant, but in terms of the kind of the magnitude, it's not that big. The one standard deviation increase in the in milk productivity of the cows produces an 8% lower likelihood of exiting. So on average, really, most dairy farms are heavily into dairy. You guys probably, this audience knows that. The reasonable changes in how important dairying is don't really make that much of a difference. And then whether you're a grazing farm or not does not change the likelihood of exit. That actually was somewhat a surprise to me. I thought perhaps that this was a period where grazing farms might have been more likely to stay in business, but no. All right. So we then tested regional differences. The important thing to see here is that there are only stars up here on the things I've been talking about, and none of these things are statistically significant. So that Rorschach test that you were supposed to find a regional difference, you didn't find any. And that's correct, that this is all over the state. So then we say, well, in 2003, we actually asked these farmers, like, what's your probability of staying in business? And so actually, as a researcher, it'd be really nice if people were really good at predicting their futures. Because then we could ask them today, what's going to happen tomorrow? And we could predict what happens tomorrow. And, that's great. This is kind of a useful thing. Actually, in this literature, almost nobody does this kind of retrospective thing that you're seeing here today. Everybody just uses predicted. Like, we asked the farmers, are they going to stay in business? And they all said they're going to leave. But if people aren't always good at predicting that. So let's see, if we had just used what they said in 2003, what I would have told you is that farmers' age is the only thing that matters. So older farmers were more likely to say they're going out of business, but it wasn't related to the size of the farm, the number of cows, how productive they were, or the other things that actually turn out to matter. The other thing, so let's think about, like, how accurate were they? So we asked them, are you likely to stay in business? And we can observe whether they actually did. So those that say, I'm unable to continue in 2003, or I'm already out of farming, were 30% more likely to exit. So they were sort of good predictors, but 30%, that's like, I'm going to be out of business next year, and 15 years later, you're still there. The same kind of thing with this sort of 1 more year, 2 more years. Those that said, oh, I could stay indefinitely are 20% less likely to exit. But that's still actually not a very high number. So again, the likelihood that a farm exits the dairy business, they said they were planning to exit in the next 5 years. Those people were 10% more likely to exit. So that's not a very accurate prediction. So what this suggests is that some of these things, low productivity, smaller farms, dairy farms that aren't focused on the dairy business are more likely to exit, as are older farmers. Some of the things that we thought might matter, like grazing or ownership type, or even these regional variations. I started this work with a set of priors about, I won't tell you what regions I thought would have more exit, because I was wrong, and there's no point in telling you all the ways that I am wrong. But we really, I think, did expect something, and we didn't find. But I think what maybe is more important is that exit is actually really hard to predict, even for the farmers themselves. And it also seems like this suggests that maybe the exit is driven by larger trends, other things than the specific characteristics of those farms themselves. So it's not that, oh, if you have a 150 cow dairy, you're more likely to stay in business than a 50 cow dairy. Yes, you're more likely to stay in, but the big movement is likely to be other things going on. And so the kind of larger changes in the industry are the things more likely, like larger changes to profitability are the things more likely to affect this. And then kind of a methodological point, that both farmers and us as econometricians are not actually that good at predicting exit. And that, I think, matters to how we think about, like, survey data that says, 20% of the dairy farms are predicting that they will exit in the next 2 or 3 years. Well, that one should take that with a bit of grain of salt to that. It's also sort of disappointing that I'm not going to run out and do a survey of dairy farms and say, we might ask this question, but I'm not sure I'd really believe it, of like, how likely are you to stay in business? Because I think there's a lot going on these farms. So that's my story.
So we have time for a few questions. You need to use the microphone because I have been told it's being recorded. So I'm going to go first here.
So Jeremy, one of the questions I have is that what's the next question is then, what happens on those farms? Are the farms sold? Are they doing something different? So I'm just, I mean, yeah, I know that wasn't it, but just any thoughts on that?
So we have, I need the microphone too. So we haven't really looked at that. And I mean, I think I have lots of sort of anecdotal stories, and in general, where there are dairy farms, the demand for land is quite high. So we should expect that a lot of that land is still in the dairy business. What we don't have, and I'm not really sure how one does that would do this, is actually understanding the land base. So we have a small farm that goes out of business here. There's a larger farm here that incorporates that land. Do we see that? Or does, certainly there are farms that go into raising cattle that are non-dairy. That's certainly a path. But we don't have a way of knowing how much of that there is.
Hi. Actually, to follow up on that, but I assume you don't know the answer, is because of those diversified farms, I was wondering if they are actually just then focusing on one of the other products that they're producing that might be more profitable because what maybe their dairy is really small and no one wants to or can go there and get that milk. But then also to follow up on something else is, did you account for any geopolitical situations, socioeconomic, even just the commodity trade market volatility of prices and things like that?
So I'll start with the volatility. I think that's a lot of what's driving this. We don't observe these farms year by year, which would be an interesting way of doing that and seeing if, okay, we actually see these exits, particularly in bad price years, or maybe it's a year after that or 2 years after that. And I think that would be an interesting thing. It's a little bit hard because our lists are not fully accurate in a kind of, this farm is absolutely milking cows at this moment. And on the longer term, we think it's reasonably accurate on these kind of long-term trends, but not that accurate on kind of year-to-year trends. Wait, your first question was. Oh, yeah. So actually there are precious few really diverse farms. Like dairy is rather all consuming. I think your supposition that, maybe, you're growing ginseng and the ginseng market's going really well, so you get out of the dairy business. That, I think that is a possibility. But I think there's actually relatively little of that. Like if you're milking cows, the idea that, oh, hey, let's just go do this other thing is not that frequent.
I think he was first. I'll go.
Yeah, thanks. Yeah, this will be very quick. Is there a firm definition of what a CAFO is? And if so, if an operation is a CAFO, does that have any impact on its likelihood for success or for having to exit?
Okay, so a CAFO is actually defined as 1,000 animal units, which is generally about 750 cows. Somebody can, depending on how you measure what kinds of cows. We don't know who we have scale. So what we have is this sense that larger farms are more likely to stay in business. That would include ones that are more than 750 animal units. So I guess on that point, yes, this is consistent with them more likely to stay in business. I think one caveat is that we have relatively few CAFOs in this original survey in 2003, and so more of that has been farms that have entered since. And since we didn't observe them in 2003, we can't really say what's going on there.
Okay. Thank you, Jeremy. That was really interesting. So I have a two-part but still short question. So the first is, I was wondering if you're planning to do another survey, because it would be interesting to see like post USMCA and the kinds of other changes that we're seeing now. And also with the continuing of exit. And then the second part of that question is, did you, or would it be interesting on this potentially future survey to ask the farmers why they choose to exit on the survey?
The second part, yes, it would be nice to know that. We actually, I think for 2003, we do have some of that information. We actually have sort of succession plans. Like, do you have a succession plan? I don't think we have the, like, if you're going to exit, why, which would be an interesting thing, assuming they're actually good at estimating that, which I'm not so sure. My sense is that the sort of exits have continued more or less apace. And I don't know that I think a next thing we could do is at least try to look at it sort of year by year related to sort of price differences.
Okay, we're running out of time, unfortunately, so we need to go to the next speaker, and Jeremy is gonna introduce our next speaker.
All right, so now I'll turn it over to Jalyssa Beaudry. She's a graduate student in Ag and Applied Economics and is mentored by Chuck Nicholson, who's a member of the Dairy Hub here at UW-Madison, as well as this has worked with several collaborators at River Falls. Let's see, she earned her bachelor's degree last May from UW River Falls, and is now a master's student here at UW-Madison. Jalyssa grew up on a small dairy farm in Minnesota and has had internships with Compure Financial and Dairy Farmers of America. Welcome, Jalyssa. Take it away.
Perfect. Thank you, Jeremy. As he said, my name is Jalyssa Beaudry. I am a current graduate student here at UW-Madison. And in my undergrad at River Falls, I graduated last spring. I started doing research on automatic milking systems. And so today I will be presenting on assessing the use of automated milking systems on Wisconsin dairy farms. My co-PIs are Dr. Shahir Birney from UW River Falls, Dr. Luis Pena-Levano from UC Davis, and Dr. Chuck Nicholson from UW-Madison. So a little bit of background on automatic milking systems. They're also referred to as robots or robotic milking. And so they allow the cow to get milked without the farmer ever having to be in the barn. So the farmer can be in his house, on a beach. He doesn't have to be in the barn with the cows. The first robots in the United States were introduced in 2000, with the first farm adopting them being in Wisconsin. And the reason why they're important is because it's a major change to the dairy farms here, and it can affect farm productivity, animal welfare, and the farmer's quality of life. But the research on this is pretty limited. There's not a lot of research on the use and impacts of AMS in the US. So that's kind of why my research is important. That's a picture of what an AMS looks like. UW-Platteville has them on their farm. So pretty cool. For our project, our overall objective was to understand patterns of AMS use by Wisconsin dairy farms. We did this by breaking it up into 4 questions from our survey data. So we asked, what are the characteristics of AMS users compared to non-users? So from our data that we got, we split it up into 3 categories: people that are using AMS, people that are not using AMS and not considering AMS, or people that are considering using AMS. And then we asked, what impacts do AMS users and non-users perceive? What factors are associated with AMS use? And what are the impacts of AMS use on the number of hired workers? The method that we chose for this was a survey. We sent a survey out to 2,000 dairy farmers in January of 2023. We got 673 responses, which is about a 33% response rate. So it shows that dairy farmers are interested in learning about automatic milking systems and future technological integration into the dairy industry. From this data, we did a descriptive analysis of farm characteristics and their perceived impacts. And we did a limited dependent variable model to assess factors associated with use and hired labor, including a multinomial logit model and a Tobit model. So looking at our farms' characteristics, we can see 50 farms use AMS from our 673 responses. 120 are considering using AMS. 483 are not considering or using. So in looking at this chart, we can see that people using AMS, they have higher number of cows, higher milk production per cow per year, and more land owned and rented. But the labor is not statistically different. It is interesting, however, to point out farmers using AMS have more cows, but the same number of employees for full-time and part-time employees. Compared to people or farmers not considering and not using AMS, they have about half the number of cows with the same amount of laborers. And then, so looking at farmers' age, their distribution, we do see that farmers 55 years and older are neither considering nor using AMS, which may be because they're on the edge of retirement, or as Jeremy was talking about, leaving the dairy industry. We do find that people 45 years and younger are looking into using AMS, either considering or already using, which may show that they have more of an openness to technological integration on their dairy farm. We then looked at the reported adoption by year, and it seemed pretty consistent from 2013 to 2020. In 2020, we saw a dip, COVID-19 pandemic, the economic pressures as well. But then in 2021, there was a spike, probably due to people not adopting in 2020. They made it up for it in 2021. And 2022 is the last reported year. It seems it went back to the average that it was before COVID happened. And so when most users they purchase 2 to 4 robots. And just for cost reference, it's about $250,000 to $300,000 per unit. So for 1 unit, that's how much it costs. And most users are purchasing 2 to 4. Then we asked people that have AMS on their farms, we asked them, why do you use AMS? And the top reason, just about 80% of them said it was to reduce labor dependence. And so labor, there's been a shortage of labor, no matter what industry you work in. We've seen that through the COVID-19 pandemic and beyond. And so 80% said that they wanted to reduce their labor dependence, and that's a main motivation as to why they adopted. They wanted to improve cow productivity, milk yield, replace their current milking system, meaning it was outdated or it wasn't fitting their needs or it wasn't super efficient for them, and then reduce management time. So some previous studies that I've done shows that your management style really shifts from being a cow person to being like monitoring your cows from your phone or your computer with AMS. Some perceived impacts of adopting AMS. So again, these are just the farmers that have AMS. They said that it improves their outlook on their farm's future. So meaning they're not worried about being there in 10 to 20 years. They have a pretty positive outlook on their future. It increased the amount of time spent with family members, which is kind of huge. I mean, most of you guys know dairy farmers. I've known some dairy farmers that switch around their schedule so they can make it to their kids' basketball games or soccer games or whatever. So this having AMS increased their time spent with their family members. And then just an interesting point, improving mental health or stress was less than 50% of AMS users said that. And so when thinking about mental health, it's not really a first thought when it comes to thinking about AMS improves mental health. Some of the top reported reasons for people not using AMS or not considering the use was cost. The top 2 reasons were it was too expensive to purchase and install. And like I said before, it's $250,000 to $300,000 per unit. And then once you install that unit, along with the cost of retrofitting or building a new barn, you have to maintain that robot that you purchased. So that was the first and the second reason as to why people are not using AMS. Another reason was that their herds are too small to justify that investment. Another reason was that 25% of farmers are satisfied with their current systems. And for people that have adopted AMS, that was a large motivation, was that they weren't satisfied with their current system. And then another interesting point is that less than 10% have access to plenty labor, which shows that we have a labor issue in our industry. And then looking at what factors are associated with AMS use. So we found a positive association between farm size with land owned and rented, but not the number of cows. So if you have more cows, that doesn't mean that you will have AMS or not. We found that for every 1,000 acres, your probability of having AMS increases by 3%. If you have a nutrient management plan, your probability of having AMS increases by 12%. And we also saw that having AMS means, or has a positive association with reporting large wage increases in recent years. We found a negative association with AMS use with the age of the respondent. There was a linear effect with that, and reporting beef production as well. Some of the factors that we found that are not associated with AMS use were cow numbers. Like I said before, we had farms that reported 4,800 to 3,500 cows in our survey, so cow numbers were not associated whether you had AMS or not. Reporting other production activities and being certified organic, we only had one certified organic farm that reported using AMS with our survey data. Off-farm employment by household, whether you have AMS or not, we found farms, all of the farms have off, or not all of them, but it didn't matter if you had AMS or not for off-farm employment. Reporting smaller wage increases in recent years, it didn't matter as well. It was not associated with AMS. Then we asked, does AMS affect the number of hired workers? We found no, it's not statistically significant with the association of AMS with full-time employees or part-time employees. We found cow numbers, wage rates, and reported difficulty of retaining workers were statistically significant when associated with full-time and part-time employees. So this leaves the next question as to what are employees and workers doing if they are not milking cows. So that's a future work, hopefully for us to do in the future. In conclusion, from the picture, do cows love robots? Do robots love cows? I'd hope to figure that out in future research. But some of our key findings were the differences in the characteristics of AMS users and non-users. Farms are reporting positive impacts when they have adopted AMS. Costs are a key impediment to adoption. Like I said before, non-users find that the cost to purchase and install is one of the biggest reasons they haven't adopted yet. And our future work, we want to look into the labor use. So we find there's no statistical difference in labor use. And so what are farmers or employees doing if they're not milking cows on the farm? And then a broader evaluation of the economic impacts is also needed. So another thing to look for in the future. Thank you.
Thanks for the presentation. So we are open for questions now. We have some time. I don't see many hands yet. Oh, I see some hands. Great. So let's start with Gustavo here.
Very nice presentation. Thank you so much. You showed that there was an association between people perceiving as like family friendly doing robots, but you didn't see any change in the labor. Do you have any data regarding hired labor versus family labor, and how does that impact on the adoption of AMS?
Yeah, we don't have much data on that. It's kind of hard to because some people will say that they pay their family and some people won't pay their family, or, child labor, that too. So we don't really have any data on that.
Here, next.
Jalyssa, I know of a couple of farmers that have both a parlor and a few robots. Did you have any complications compiling data because of farms that have more than one system?
Yeah. So when we wrote our survey questions, we asked if they had automatic milking systems, and if they did, we classified them as having automatic milking systems. So if they had a parlor, almost all their data went into AMS.
Thanks for the talk. I'm just curious about, I guess, two things. One, how do the cows like it? I have no experience with that. And does it increase the electricity bill of farms?
Oh, yeah. I would say cows like it pretty good because they can be milked at any point in time. It's on their schedule. And most of the barns being built, I guess I didn't mention it, but cows are incentivized to go to the robots by being fed pellets. So most of the time they get a treat when they go to get milked. And what was your second question?
The electricity bill.
Oh, yeah, electricity bill. I don't have any research on that, but I do know that when farms implement AMS, they do have to have a backup generator. And that goes into, it's a new field of animal welfare studies as well, because if the power goes out, cows aren't being able to be milked. That's why farms have to have a generator so the cows can be milked.
Nice. And then just the last thing, you showed that the larger farms with the milk robots have a greater milk output. And I'm just wondering, is that because of the AMS system, or is it because it's a larger, more efficient farm, or both?
Yeah. Yeah, some of the previous research that that I've done before has shown that like farms, when they switch to AMS, if they're milking 3 times per day, they don't see as large of an increase in milk production. But farms that are milking 2 times a day and then they switch over to AMS, they see a higher impact in milk production yield.
Any other questions? I see one. No, but we need them. How many farms are in the state?
Oh, yeah. Yeah. About 8% of herds in Wisconsin are using AMS.
Any other question? I see over there. Good. I'm glad to reach you this time.
Thank you for your talk. When you talked about labor on the different sizes of farms, was that strictly in terms of the number of full-time equivalent employees, or did you look at it in terms of full-time employees per animal unit or per unit of milk production?
Yeah, it was per animal unit. So 1.7 labor's full-time employees per animal unit.
Any other questions? I have one question actually. Very interesting the part that you said that one of the motivations to do AMS was reduce the labor on the farm. But seems to be that when you actually ask them, those who actually have AMS, they didn't save labor. Can you comment on that?
Yeah, that's where we want to explore more into what farmers and employees are doing if they're not milking cows. So did they expand their land base? Because we did see a positive association with for every 1,000 acres, your probability of having AMS increases by 3%. So that's something that I do want to look at in the future.
Okay. Any other questions over there? Great.
Thank you so much. It was a great presentation, and I have about 50 questions, but I'll stick to one, which is, did you look at all into the kind of connection of putting in AMS and pasturing? Because I don't know if you're familiar with like Lewis Holloway's work in the UK, but he's written extensively about AMS and ideas about freedom in cows, but also this kind of idea that cows would go to the milker themselves, but it also really depends on how much pasture they have access to and what kind of farm system. So I'm just kind of curious whether you're looking at that or if you plan to look into how putting in these systems shifts the use of pasture versus stored feeds.
Yeah, from our data, we only had one farm that was organic, and most organic farms are pastured based. But no, we didn't look at pasture. No, sorry.
Last call for a question. I see no hands, so let's thanks again, Jalyssa, for the nice presentation. Now we're gonna have a short break until 2:05 is scheduled to start the new block of the session of the afternoon. So looking forward to seeing you at 2:05 or a little earlier. Thanks. Bye.
I'll write it down. I'm sure we'll probably have Wait, so you think you yeah. So a lot of them.
So some of, I think a lot of. Like the answer. That's good. I said.
Yeah, that's true, yeah.
Yo creo que ya estuvimos acá. Creo que tanto
Yeah. And I think most of them.
mandé ayer un mensaje a Uruguay
And maybe.
porque estaba
Yeah, it might be worth even. That paragraph. Like, things we don't. That it was worthwhile.
Para una gente de la banda. Pero realmente es una chica brillante, que tiene ella, una buena soy no, ella vive pero también está trabajando Colorado hablando le había propuesto que arrancara programa ya el otro mes, como sí, dije yo, eso sería calidad, pero ella me dijo que pues a mí también me dijeron que estas son pero en sí está bueno, pero cuando tú me miras en segundo pasa es que el daño también tiene la bala está en la alianza. Porque es como parte de ese pueblo. Bueno, entonces ya, si no puede hoy, mañana también. Para el viernes pasar en el edificio. Ayer la pasta lo era todo para que así no es colombiana, para que vale, porque la verdad que me pareció como se viene el mindset que pueblo para que no, extraordinario. El viernes va a ir a la pasta de el yo creo que va a ser más poco la tarde. Porque al mediodía no se da no después la tarde pasamos. Si le interesa, se aparezca la video, que haga todo lo que no, pues yo te la presento, y tú le sacas información, o para que la más ahí con el claro, me mencionas un poco cuando ya no está. Bueno, gracias a que después, ahora se llama Lo voy a hacer acá para que no te tengas que desmontar allá y dentro. Ah, bueno, bueno. Estamos recolectando fondos para usar. Voy a buscar
Yeah, we are last year. One third. Yeah. Oh, 1/3. 40. That's another language that learn since Asia is so great.
I've had a fluid, I forgot. But I found the fraction here. But I had a bad.
So you learn proficient, right?
Yeah.
Like you can say, I
haven't focused. I can say like. No, I feel like it's better than my.
Here's our.
I like this role with this banking.
The building we were in last year. I think there was
What about cozy? I love this.
I think so. You know, after like.
Well, oh yeah, that's the excuse.
Oh, I couldn't put my hand. I should have. We were around.
Yeah, that's Looks like capital there. Thanks that I wanted to see.
So you saw some of the competing patterns.
So yeah.
Race Enzien.
Basically cows that turn out to be
Right.
right after. Yeah, so there is the kind of one.
Big name there.
Salmon has like 5 different.
I mean, I actually.
I think we should get going for the second part of the session afternoon. So it's my pleasure to welcome back all of you and welcome especially our next speaker. Her name is Gracie Enzien. I hope I said. She's a PhD student in bacteriology, mentoring by Tom Donahue in the Great Lakes Bioenergy Research Center. So welcome to Grace. Please, the floor is yours.
Hi, before I start, I just want to give a land acknowledgement that Madison sits on native Ho-Chunk land. I just feel like that's important for us to also know. So what I'm going to talk about today is a very underutilized waste stream in the form of dairy co-products or dairy residues. I will use that name interchangeably, and how we can use this waste product and convert it into value-added products through microbial fermentation, in particular, dairy residue fermentation into designer D-lactic acid. So, as we're all aware, the Wisconsin dairy industry is vital to the Wisconsin economy, generating roughly $46 billion to the state economy each year. There we go. But in doing so, a lot of waste is produced, one such waste being dairy co-products. For reference, 85 to 90% of milk by volume is discarded as whey. When we look at different types of dairy products that are made, co-products are made also. So for example, when you make soft cheeses such as cottage cheese, you're also going to make cottage cheese acid whey. If you make Greek style yogurt, you're going to make Greek acid whey. Or if you make hard cheeses, you'll make sweet whey. There's also ultrafiltrate milk permeate from ultrafiltration of milk. So these dairy co-products are rich in the organic matter lactose, and because of that, they're hard to break down due to having a high biological and chemical oxygen demand. What I mean by that is a lot of oxygen is needed in order to break down these sugars. So if you spread this into rivers or streams, you can affect your aquatic life. If you spread it out on crops, you can affect your crop yield. So really, there's only two kind of viable solutions at the moment. You can use it as an animal feedstock, or you can undergo expensive wastewater treatment. But like I said, these dairy co-products are rich in lactose, but also other essential vitamins and nutrients that microbes love to eat. So instead of treating this like a waste product, why don't we use it as a new feedstock to feed microbes? This comes to my project. I'm specifically interested in the production of designer D-lactic acid through the genetic engineering of my strain, Lactobacillus plantarum, WCFS1, which I will just call it L. plantarum for short. For reference, this is D-lactic acid. And D-lactic acid is important because it is a billion-dollar industry in its own self, but also more importantly, it's a precursor for the biodegradable biopolymer polylactic acid. Like stated earlier, I'm co-advised by Tim Donahue and Daniel Guerra. They're both part of the Great Lakes Bioenergy Research Center, where our goal is to take different types of waste in the form of, in my case, dairy co-products, but in other people's cases, plant biomass and converting it to value-added products. One reason is we want to be less reliant on fossil fuels, but we also want to be able to reduce the costs of making these bioplastics. Because as I like to say, money talks. So like I said, I'm making the precursor of polylactic acid, which is D-lactic acid. And polylactic acid is made through this chemical process of condensation, where it will go an intermediate of making lactide before going through a opening polymerization to make polylactic acid. Why am I using dairy co-products? I've like told you, it's a cheap source of lactose that microbes love to eat. Instead of using expensive glucose, why don't we just take advantage of something that's abundantly available? So this comes to how I went about genetically engineering my strain. So my strain, L. plantarum, is a heterofermentative lactic acid bacteria. What I mean by that is it uses both the glycolytic pathway and the phospholipase pathway in order to break down lactose into pyruvate and then further into other fermentation products such as lactic acid, but also ethanol and acetate. So just imagine that you have a lactose molecule up here. It's going to be broken down into glucose and galactose through, again, either glycolysis or the phospholipase pathway. This will further be broken down into pyruvate. Pyruvate can then be converted either into L or D-lactic acid. L and D-lactic acid are stereoisomers of one another. Basically, what that means is they have the same physical and chemical properties of each other, but they're mirror images. They differ by their chiral center right here. So L-lactate acid can be made through this enzyme known as L-lactate dehydrogenase. Well, D-lactic acid can be made through either D-lactic dehydrogenase or lactate racemase. Basically, when there's excess L in the cell, they will convert that to D-lactic acid. As in my strain in particular, D-lactic acid is vital to the cell wall. So it was pretty easy for me to just, I say easy, but it was a lot of hard work. All I had to do is delete the gene for L-lactate dehydrogenase in order to make a strain that produces just D-lactic acid. So now we'll go into some preliminary studies we did. So this is using MRS media. It's a laboratory media that is selective for lactic acid bacteria, such as my own. It uses glucose and other like essential vitamins that microbes like yeast extracts, beef extracts. But as we'll get into later, those are very expensive to add. So this is my wild type strain. So this is a strain that does not have the deletion of the L-lactate dehydrogenase gene. Well, this is my mutant strain that does. So in both cases, at about 24 hours, all of the glucose is consumed. In the case of wild type strain, there's about a 50-50 mixture of both isomers produced, which is to be expected. While in my mutant strain, you can see it's just D-lactic acid. Also, I should point out that they also do both make some other end fermentation products, and that just means acetate, ethanol, what have you. So I've shown you that it can be grown in laboratory media, but what about dairy co-products? So we recently, I should say, we used to use a different type of dairy co-product. We used to use cottage cheese acid and ultrafiltrated milk permeate. And I had done studies in batch cultures with these, but we were running into issues where not all the lactose was being consumed, and that was partly due to not being able to control the pH. We added a buffer, but as you will learn through this experiment, bioreactors are a very nice tool to be able to control both the temperature and pH, as well as control anaerobic environment. So we were recently gifted these two new dairy feeds, which I will just call dairy A and B in order for confidentiality reasons. They are 4 times as concentrated in lactose compared to ultrafiltrated milk permeate. So what we did is we took these feeds, set them up the same way. We put them in a bioreactor, and then we set the conditions to have a pH of 6 and a temperature of 37 degrees. Basically, base was added in order to maintain the pH. And once no more base was added, that told us, okay, no more lactose is being consumed and no more products are being produced. So from there, I should step back a little bit. The reason we're doing this is because we don't know if there's any microbe present in this feed. So the reason we're setting this up is we want to know if there's something growing in there, if lactose is being consumed, and what other products are being made. Is it lactic acid? Is it ethanol? Is it acetate? So after we did run this, we were able to do different analysis, such as chemical oxygen demand, which allows us to measure how much lactose is being consumed, as well as cellular growth. We were able to measure the total nitrogen to, first of all, figure out how much nitrogen is present, because cells need nitrogen to live. And we can also see if it's being consumed. We were able to measure protein as well. And we were able to measure the actual sugar through HPLC equipped with an IR detector. And this was done by the metabolomics group that are part of GLBRC. And then I also measured my samples using a biochemical analyzer in order to determine L-lactic acid. So after about 168 hours, all of the lactose was consumed in both dairy feeds. However, when we look at dairy A, the majority of the fermentation products is the majority of the products produced, while there is some L and D lactic acid produced. While in dairy B, L-lactic acid is actually the major fermentation product produced. So what does this data tell us? There's obviously some type of resident microbe or microbes present in our feeds, and they are able to consume lactose and produce fermentation products at the same optimal conditions of our microbe. So where do I go from here? Where do we go from here? Well, first of all, we need to figure out what exactly is inside these feeds. That's why we will perform 16S RNA sequencing, which is a technique to determine what type of microbe or microbes are present. And that will allow us to either outcompete these microbes or utilize them to our advantage. So what I hope you got away from this is the fact that our mutant strain, at least in laboratory media, can produce exclusively D-lactic acid, and that these dairy feeds will provide us with a lot of lactose in order for our microbe to eat them and ferment them to make value-added products. Like I mentioned, we're going to perform 16S RNA-seq in order to determine what microbes are present. We also are going to analyze, we're going to feed both our wild-type strain as control and our mutant strain in these two new dairy feeds set up at the same bioreactor conditions that we did just the feed itself in order to see if there's a difference, is lactose still being consumed at the same rate? Is more lactic acid being produced? And then from there, we can go ahead and optimize the titer yield and rates. These are very simple experiments. We're just doing what we term batch bioreactor. It's literally just throwing the feed in and either having inoculum or no inoculum, and then figuring out what's being produced before we eventually go on to doing fed batch bioreactors and using a membrane that my other lab mate has used. In addition, my undergrad Annika Grace Klein is working on another mutant that produces solely L-lactic acid. And the reason for that is, I forgot to mention, but basically D-lactic acid is underutilized in the market compared to L-lactic acids. That's why we did start with D-lactic acid. But in order to make polylactic acid, you want optically pure L and D. You don't want a racemic mixture, and you don't want just L and D alone. And the reason you want to do that is it increases the properties such as thermostability and mechanicability, because we want to lower the cost, but we also want to be competitive with fossil fuel-based plastics. So with that, I want to acknowledge my funding sources, the Dairy Innovation Hub, the Dairy Business Innovation Alliance, my lab mates in the Donahue Noguera Lab, my committee, Tim, Dan, Victor Uger, Trina McMahon, the Microbiology Doctoral Training Program, all my collaborators in this dairy industry. Special shout out to JP over in food science, his staff scientist, Ji-Hwan Oh, and Mike Multier over in the Center for Dairy Research. And for that, I'll take some questions.
Okay, I see one hand here. Let's start with her.
Oh, thank you, Chris. Great presentation. I'm just wondering for your feedstock. So you mentioned different kinds of whey, but are you using whey or lactose as your feedstock at this moment? Are you trying to look at different kinds of sources and different, sources with different prices?
So no, we're using the lactose in the whey itself. I don't know if that.
What that mean? Is that pure lactose derived from whey, or it's the
So
whey strain?
it's like the whey that is given to us by like different dairy partners, like the milk water itself. We just use that, and that's what we feed our microbes. We don't like dry it out or anything.
Thank you. And another quick question is, you mentioned you are going to use a bioreactor, right? Is that going on, or you plan to do that? And what's the scale it will be?
Yeah, so sorry if I didn't clarify that well. So basically for the experiments using like laboratory media, this was done in just standard test tubes. And then with these 2 new feeds where we were just growing the feed itself, it was in batch bioreactor. Like we weren't taking any influent out and effluent in, or influent in, I should say, and effluent out. We were literally just growing it to see if anything grew. And then I have used Dairy B, which I'm calling Dairy B. And I've grown my mutant and wild type strain. That I just haven't gotten around to analyzing that yet. And then I need to do that also with Dairy Feed A.
Question over there?
Thank you for a nice talk. So I probably missed what you mentioned. So when the mutant produces pure D isomer, what's the substrate? Pure glucose or?
Yeah, it's glucose. In the laboratory media that I showed earlier.
That's glucose, right?
Right here, yeah, this is glucose we were using.
Did you try pure lactose?
I haven't tried pure lactose. I've just used different types of dairy residues, so different types of whey or ultrafiltrated milk permeate. I have not gone ahead and done just pure lactose.
Okay, do you think the mutant direct take lactose or hydrolyze lactose to glucose and galactose, then take them individually?
I believe it breaks the lactose down into glucose and galactose. I don't know if that.
Okay. Yeah. Maybe you can try pure lactose, galactose.
Yeah, that's a good idea. That is a good idea. I never went ahead and did that.
So you already tried pure glucose.
Yeah.
To see what happened on pure galactose.
Yeah.
Right.
We kind of just went straight ahead to the dairy co-products.
Yeah. Thank you.
Thank you.
What is the optimum pH for those strains?
Yeah, so for my strain, L. plantarum, the optimal pH is 6 and the temperature is 37 degrees. Lactic acid is pretty acidic. So my microbe can survive, but it will stop consuming lactose and producing lactic acid. And we've seen this in batch culture. The data is not shown, but basically when I grew it in batch culture, I grew it for like 192 hours, so it's over a week. And there was still like half the lactose left. So that's why we kind of switched over to using bioreactors, because it's a lot easier to control those conditions.
And when you mentioned they stop, it's around which pH? Do you have an idea on that?
It kind of stabilizes out at like 5.6, but that's because I added a buffer. When I don't add a buffer, it will go to below 4.
Okay. Thank you.
Yeah.
Any more questions? We still have a minute or two. Great.
Thank you for the presentation. You talked that the cheese industry has about 80 to 85% of waste, or they have to use something with that.
Yeah.
With this, what kind of product do you come up with, or does it use the whole whey product, or is there another, I guess, something that's left over?
If it's able to consume all the lactose present, we're assuming it's using all of the whey product.
So you're using 100% of whatever that product was. Okay. Then second question, are you able to patent your strains?
We are working on that right now because we do have some interested partners, but we're kind of being hush hush right now.
Thank you.
Thank you. I think that concludes this talk. Jeremy, do you want to introduce the last speaker?
All right. Thank you, Grace. It's now time for our final speaker. Xiaolei Shi is a research assistant in chemical and biological engineering at UW-Madison. She works on dairy projects and food regulations, and is the funding regulatory lead on the UW-Madison project on turning acid whey into value-added products. Please welcome Xiaolei. Thank you.
Okay, first of all, please forgive my cracking voice. I got a cold a few days ago. The cold has gone, but my voice didn't come back. So please tolerate that. And also, as Jeremy mentioned, I'm like a food scientist working in the chemical engineering department. But except for that role, I'm also a specialist for translational research. So I know, Grace, you have interest on IP stuff. I'm not an IP person, but if you have interest for, NSF Corp or other programs on campus, I could be your first stop for those efforts. So in the past 2 years, I have been pretty busy working to help a project which is about the upcycling of acid whey. So this project has a plan for commercialization. And first, I want to really introduce you to our awesome team. So for this project, we have 2 research leads. Dr. George Huber, he's a catalyst expert. He's in the chemical engineering department. And Dr. Scott Rankin, he's a dairy science expert. He's also here today. And we have a CEO of the newly founded company, which is called Jalyssa. Mr. Gerald Featherman, he's the CEO and also our entrepreneur lead. So as for myself, I'm the technical lead, and also I'm helping with the food regulations as well as fundraising for this project from both the government as well as in the future will be from the capital ventures. And also we have research and development lead, Dr. Wang. He's doing daily experiments in our lab. And we have advisors and mentors across different backgrounds to help with this commercialization journey. So to talk about our project, first I want to bring up about the problem we're solving is a real world issue. Grace has talked about the acid whey, but to summarize, actually acid whey can be defined as the waste stream of the Greek yogurt and acid crucular cheese production. The acid crucular cheese could be cottage cheese, for example. So if you look at all the acid whey, the biggest issue is the Greek yogurt acid whey, which accounts about 3 million tons per year in the United States. And also it's about 80% of all the acid whey produced in the United States. So if we can handle the Greek yogurt acid whey problem, we can pretty much carry it over to other acid whey streams. As for its composition, I will show you later, but here I just want to mention, acid whey is pretty high in its acidity. When we source from different sources, the pH could be from 4 to 5, so it's not neutral or even close to neutral. And it has very high mineral contents, which can, impact the handling of this acid whey stream. The mineral content could be, calcium, that's the major one, but could also be other minerals, phosphorus, and so on. As for the current disposal methods, there is no universal handling or treatment method, but there are some commonly adopted approaches for now. For example, the acid whey can be treated as the wastewater using such as reverse osmosis method. But what we should do with the concentrated acid whey? As Scott always mentioned, we can probably just dump it out of the window, but it won't reduce the environmental impact. And also, the acid whey can be used as the animal feed, but it's pretty high in its acidity, right? So it must be blended with other animal feed before being offered to the animals. And from this picture, we cannot tell, but I bet the pigs are not quite happy about eat those acid whey directly. And also, the commonly used method nowadays, especially for like the big players like Chobani, they're just paying, the local farmers to pick them up. They give the credit at about $18. This is average per ton for them to pick up. And as we can see from this image, they're just dumping on the land. So that can cause a lot of environmental issues, especially water pollution. So our team is really thinking hard about how to handle this problem. So based on our expertise, we decide we can upcycle this acid whey into some valuable ingredients, especially some food ingredients such as sweeteners. So on this slide, I just want to show you that the acid whey, the Greek acid whey problem is a surging problem. So if you look at the data a decade ago, it only took about 1% of the US market, right? But now, by 2020, it took over half of the US market share, and it's still increasing. And I want to mention that about 1 pound of the Greek yogurt will produce 2 to 3 pounds of the Greek yogurt acid whey. So that there's a lot. The reason is when we make the Greek yogurt, there is a process called straining. So the excessive water is being removed after the fermentation. And the water is not just water, it comes out along with lactose, minerals, and some other compounds of the dairy. And that can cause a lot of problem. So here on this table, I want to show you that there is no universal treatment of the acid whey, but those big companies as well as some research studies have took some efforts to handle this acid whey. I'm not going to go through all of them. Let's just look at just a few of them. Such as a big player, Chobani, what they are doing is they use reverse osmosis method to treat the Greek yogurt acid whey to get it concentrated, but they still need to handle with the rest. So it didn't reduce the environmental impact. And also, as I checked, General Mills, they filed a disclosure of an invention around using bioconversion method to derive the fibers from the acid whey. But there is no further commercialization after the disclosure. So it's not being scaled up yet. And also, if we move down, we can see, recently in the past few years, there are various laboratory studies. They use enzymes or microorganisms to produce a sweetener, which is called glucose-galactose syrup or other similar names. This is the hydrolysis from the lactose. So, but this method, when they use enzyme, it will, have a very high cost of the capital and running, and also the enzyme is slow, right? So it will take maybe 12 or 24 hours or even days to get this process to finish. So that's a very long time and low yield. And also think about if we use enzyme method, sometimes the body of the acid whey will be exposed at ambient or slightly elevated temperature. That can cause a lot of hygiene problem, such as that can promote the growth of the spoilage or pathogenic microorganisms. So that's a concern for us. So based on that, we want to propose our unique non-enzymatic method. So here is our overall goal. So we are working very hard to establish a catalytic approach, which is non-enzymatic, to valorize the acid whey into the value-added products, especially sweeteners. And at the same time, the key thing is we want to mitigate the environmental footprint. So we have been very successful in developing the laboratory, inventions around it. So this is the continuous lactose reactor we use in our lab. It was able to produce 1 liter of the sweetener at the laboratory scale. But now we have purchased a new lactose reactor. This is just a conceptual tool. Image is not a real one. So, but with this new reactor coming forth probably by the end of this month, we would be able to scale up the process by a factor of 100. So I will show you more information about our facility later. So this diagram shows us the overall process we're using to make our products. we all know that the Greek yogurt acid whey is from the dairy producers. And then before we get our feedstock or our waste stream, actually, usually they conduct the ultrafiltration at their facility. That's because they want to recover the proteins and the fats. They're at high value, right? They can sell them to make profits. So the one we received is called acid whey, but actually it's unproteinized acid whey. So we start from here at our facility. So the first step we do in our facility is to pump the acid whey through a nanofiltration system. So over there, excuse me, sorry. So for the nanofiltration over there, the organic acids and the monovalent cations could be removed from the permeate. And then it could be further concentrated before disposal. But the stream we get out from it is still high in acidity. The pH is around 4.6 as we measured, and we need to get it neutralized before further handling. So typically, we use the potassium hydroxide or sodium hydroxide to bring the pH up to about 7.0. And after the neutralization, usually those minerals, especially calcium, could be precipitated out from the permeate. So we got the solid particles. We'll let it go through a unique equipment, which is called a hydrocyclone. So we use the one from the Center for Dairy Research. Over there, it's by using this equipment, it will be able to separate out those milk minerals, partial of it, and then crush the large particles into smaller particles. And then we will let our stream to go through a diafiltration system where the lactose-rich stream could be separated from the calcium-rich stream. The calcium-rich stream will go through a reverse osmosis for concentration, and then it will be dehydrated by a spray dryer or cabinet dryer for removing of the water. And then we can get a white powder, which is our first product. We call it milk minerals. So as for another lactose-rich stream, we use it as a feedstock to make the sweeteners. So over here, we will let it pass through a cation exchange resin. It looks like a column. Over there, the pH will be reduced down to about 1 to 2. So the next step, the acid hydrolysis could occur. And then this low pH stream will go through a lactose reactor. So over there, the lactose will be hydrolyzed into smaller sugars like glucose and galactose. And then this hydrolysis in exchange resin, over there, the pH will be neutralized to about 7 or slightly acidic. And then it will go through an evaporator where the water will be removed. And our target total solid is around 55% to 70%. And then the stream will go through activated carbon. Over there, the color pigments as well as other impurities will be further removed from the liquid. And then we will get a syrup, which we call it GGS. That's the glucose galactose syrup. So here is a table showing you the acid whey composition. And that's before we do all the treatments as I just showed before. So as I mentioned, the stream we received is usually ultra-filtered. So we can say this stream is pretty abundant in water, which takes about 94 to 95%. And also it has about 3.8% lactose. So this is slightly lower than the lactose content in the milk. And it also has other impurities to be removed during this pre-treatment process. And we can see the pH before any treatment is about 4.6, but also the pH depends on the source of those acid whey. So let's look at further into the first product we produced, which we call it the milk mineral. So this figure here showed you how it looks like. So it's a white powder. So we compared the composition of this milk mineral with a commercial product, which is called True Cow. So True Cow is a premium, milk mineral that's available, and it's processed. It's produced by Glanbia. If we look at this table, we can see if we look at the calcium content, these two products, they are comparable, even though ours is just a little bit lower. But if you look at the moisture content, our product has a much higher moisture content than theirs. But if in the future we can tailor the parameters of the spray drying process, or we switch to other dehydration method, there is potential to reduce the moisture content, and thus we can bump up the calcium content. So here shows you another product we're making from the process. That's the major product we get from acid whey, the GGS. So as for the GGS, if you see from this picture, you can see it is a brown-hued color syrup. It's pretty much viscous after we do the concentration. And also if you sniff it, it has a sweet aromatic flavor. So we intend to use it as a nutritive sweetener. As for its intended food to use it in their formula, our initial thought was to add it back to Greek yogurt or other yogurts. So it could be a clean label ingredient. If we can go through the regulation, it could be labeled as whey syrup upon approval by the FDA. We're working on that. But also it has the potential to be used for other food applications, such as for bakery, confectionery, beverage, etc. So if we do further refinement of this syrup using advanced technologies such as adsorption or separation method, we would be able to get rid of the color pigments and make it colorless. And then it will have much more broader applications in the future. So if we look at this sweetness, it has 87% relative sweetness when it's compared to sucrose syrup. So it's slightly lower, but not that different. So here I really want to mention that our GGS looks different from those GGS made with the enzymatic approach. Because when we use the non-enzymatic approach, we use high heat. The temperature we use is usually about 120 Celsius, so which will cause the formation of some heat-induced pigments. So our syrup is brown in color, while the enzymatic hydrolyzed GGS is usually yellowish, not brownish. But this can also make our product more suitable for like a Coca-Cola or PepsiCo, those beverages. So here I want to show you the chemistry behind. The lactose, after being treated using the membrane filtrations and concentration, the content in our feedstock for sweetener production is increased. So during the hydrolysis in the reactor, the lactose is broken down into the glucose and galactose. They are the major products of our process, that's GGS. But also there is formation of a heat-induced component, which is 5-hydroxyl-methylfurfural. So 5-HMF. So this HMF, in the past, it was considered a negative component formed. But nowadays, with new research proofs, it has been considered as a flavor enhancer and preservative. So in the future research, we are thinking to get it separate out and label it as a new ingredient. Oh, did I miss something? Okay. And also here I want to mention, as I showed you, when we received the acid with the lactose content was around 3.8%, a little bit below 5%. But after the membrane filtration and several pre-treatments, the lactose was condensed to be 15% right before the hydrolysis. So this will help with us with the formation of the GGS with high total solid at the end. So here I want to show you about the kinetics we used, we built up using the laboratory lactose reactor. So we use the temperature range from 120 to 160 Celsius. And we want to look at several factors. So our goal is to have a very high lactose conversion, pretty high yield of the GGS, and we want to minimize the HMF formation. So after we built the kinetics by considering all those aspects, we were able to optimize the conditions that we can use to produce GGS. And these conditions can be carried over to our next stage, which is the pilot plant production. So here we can say the temperature as optimized is 140 Celsius, pretty high. And the flow rate is 2.4 ml per minute. The lead time within the flow reactor, it is 10 minutes, and the feed pH is optimized to be 1.1, so pretty low. So at this condition, we were able to get a lactose conversion at 90%, and the selectivity of the monosaccharides at 99%, as well as a yield of the monosaccharide at 89%. So it's pretty much reached our expectation as we set up before. Okay, so here let's look at our crude GGS composition. So in our GGS product, we have galactose, which is about 35% of the total weight, and water is only 30%, which means total solid is about 70%. And glucose is about 25%. But there are still also some unhydrolyzed lactose in our product. So in the future, we want to use some, separation or fractionation method to further reduce the lactose content to further tailor the profile of its composition. And also it has humins because we use HATE, and also HMF also forms at a low concentration. This is about 4,000 ppm. It's low, but also we are thinking to further reduce HMF by using adsorption resins. So it could be non-detectable, which is comparable to the commercial high fructose corn syrup. And here I want to show you a comparison of the compositions of our GGS with traditional used nutritive sweetener, which is high fructose corn syrup 42. So if you look at this table, we can see the water contents, they're comparable. So if you look at the monosaccharides, ours it's just a little bit lower than the high fructose corn syrup. And for the relative sweetness, they are relatively comparable, even though ours is just a little bit lower. As I mentioned, we're going to get rid of those impurities in our future work. Okay, so here is some data about the sensory properties of the GGS. So I want to make a note, these data are not from our lab. So we did a literature search about the sensory properties of the GGS made from the enzymatic hydrolysis method. So here we can see when the GGS is being used to partially substitute the sucrose syrup for different food applications, such as for ice cream, soft serve, frozen desserts, and in bread and bakery. We can generally see increased overall sensory property and decreased all flavors. This has indication that our GGS really has the potential to be a good substitute for the sucrose syrup. Okay, so here I want to mention, so at our chemical engineering department, we are focusing on making the GGS and also reaching out to food industries, but we also have partners in the food science department. So our partners, they're trying to incorporate GGS into different food, applications. And at the same time, they're doing a lot of analysis on the physical chemical properties of GGS. And these are going on, and soon we should have some data to share with you on those. Okay, so here I want to show you those facilities we were lucky to use as the Center for Dairy Research. We use their membrane filtration system and their hydrocyclone to make the milk minerals, and we use the spray dryer for dehydration. And in the future, we're going to use their evaporator to concentrate our syrup. And the good news is we just spent over $100,000 on lactose reactor. It's a pilot plant reactor that should come forth in this month. If not, it should be very, very soon. And by using this lactose reactor, we're going to make about 100 liters of the GGS at the pilot scale. And once we get this GGS, we're going to send them to our potential collaborators in the food industry, such as Wells Enterprise and PepsiCo. And they're going to do some evaluations as their site, and combined with the data we can generate at the food science department here and there. So we would be able to further tailor our process, and in the future, we can make a better product that can fit the needs of the market. Okay, I know I'm presenting in the business and economics session. So here I want to show you some effort we have done so far to predict the profitability of this process. So at this moment, we're scaling up, but in the future, probably in the next 5 years, we're going to fundraise to build our first commercial plant. So the first commercial plant, we projected to be at the inlet of 1,000 tons per day of the Greek yogurt acid whey. So this seems large scale, but actually that is able to process 0.1% of the total Greek acid, yogurt acid whey in the United States. And by using our model here, we account into the disposal credit we can get from the dairy producers. And also we take into account of the sales of the GGS and milk minerals, and also the protein can be recovered using ultrafiltration. So we get a total revenue to be 19.3 million per year, which means it's high profitable. And also we deduct the total operating costs, which is calculated by using Aspen Plus software, and also the annual tax. I want to mention all the assumptions here. They are made very conservative. So we pretty much use the low end price for the calculation, which means our real profit could be even higher. And by using this, we get the annual net revenue will be about 10 million per year. And also we conducted a techno-economic analysis. So at our projected scale at 1,000 tons per year of the inlet, we would be able to get internal rate of return around here is 35%. So this is much higher than the food industry average, which is at 6.25%. And also to figure out the environmental impact of our approach, we also conducted the life cycle analysis. So we want to compare our GGS with two conventionally used sugar syrups, which are high fructose syrup in the yellow color and sucrose syrup in the blue color. So we can see that for all the three aspects we analyzed, which are the global warming potential, the ozone formation potential, as well as the water consumption potential, we can always say the GGS, which are those green bars, show the lowest environmental impact. This is what we really want to see. So this indicates our process is sustainable and also is eco-friendly. Okay, now let's make some conclusions. So we were, time up. Sorry. Okay, 1 minute. So we were able to make multiple food ingredients from the Greek acid whey, which are the GGS and milk minerals. And also we can see our approach is highly economic competitive, and also it can bring in the environmental benefits. And also for the future work, we're working very hard on scaling up of the GGS production by a factor of 100. And also we're collaborating with, CDR, Food Science Department, and the food industry for food applications and evaluation. And another key thing we're working on is to remake the TEA model. And also we want to source from other dairy waste streams to further reduce the cost of the feedstock. And also we are reaching out to a company in Illinois, and we're trying to use their advanced separation and fractionation method to separate other impurities, and also to have a much more cost-effective production. So this is acknowledgement of our current sponsors. I will stop here, and I'm ready for questions. Sorry for my voice.
Please, let's give her a hand. Thanks. Nice presentation. We're over the time, but since it seems like there is a lot of questions, we will continue with the questions. But if anyone wants to go to the other room, I think it's at 4 that starts the main session. So we will hard stop at 4 for sure.
Thank you for your presentation. My question is, from the component, you said the final GGS contains some lactose. Is there any consideration of food allergy if you use it as sweetness?
Oh, that's a very good question. So of course, if we sell it as it is, we need to get it labeled, right, and warn our customers. But as I mentioned, we are reaching out to a company in Illinois. So they have a technology. I'm not going to tell what the company and the technology now is confidential, but we should be able to separate the lactose out from other sugars. So it should be non-detectable after we use that high advanced technology. So if we can get it out, and the GGS, after we consult with the Wisconsin DAT-CAP, is not a dairy product. If we can get rid of lactose, we don't need to, label it or put it into to warn the customers. Sure.
Shirley,
Mhm.
thank you for your very interesting talk. I have two quick questions.
Mhm.
The first one is on your milk or mineral, right?
Mhm.
So what's the form of calcium in that product? Is calcium carbonate or sodium phosphate, or what's the form of the calcium?
Very good question. So we haven't do some analysis of the calcium forms. That's what we're trying to do next. But the thing about this, dairy or whey derived, it should have, it's a combination. So could be organic calcium plus the inorganic calcium, probably citric calcium or calcium lactate plus calcium phosphorate. That's just a guess. But as for the like a portion and percentage of each, we need to further analyze in the future. Very good point.
The second quick question is, you mentioned there's a 0.4% HMF in the syrup.
Mhm.
So you mentioned it could have positive result effect, for example, for preservation. Is a safe food safe?
Very, very good question. We always talk about the HMF, and we really checked on, on the regulation. So in the United States, I haven't seen the HMF can be used as a food ingredients or approved, but I saw from EU in some countries, in Europe, they have this commercial, get it commercialized, or at least it's in some countries there is considered as safe. I think there is still a long journey to make it into the market in the United States, especially use it as a food ingredient. But at the beginning, especially if we can get it separated out and work on the journey to think about you overcome the hurdles of the regulation, things like that. So we can still make it to be successful in the market. So the way we considered before is we reached out to the FDA and see the process of the GRAS approval. So you need to, have a lot of scientific evidence to approve that this ingredient is safe and prepare some paperwork. We have talked with them regarding several ingredients we produced in the lab. We are familiar with the process, so it's not something non-achievable, but we need to plan ahead.
Yes, I remember, furfural, HMF is similar to furfural. Furfural has been used to control insects.
Yeah.
Right, so that's why I asked this
Yeah,
question.
exactly. Yeah. Mm-hmm.
Okay, I think we are done and we need to go to the main room. So thank you very much for the session, and I'll see you in a moment upstairs.